Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning in to this revision video, which covers indices, index laws, and scientific notation. So let's start with indices. And firstly, understand what we mean by indices. So if I have something like this, 2 to the power of 5, we say that that expression is written in index form. So the reason it's written in index form is because this number up here, which is also called the power or exponent, is known as the index. So there is an index here. We call the other number the base. Now hopefully you know that when this is positive integer, when you're raising a number to a positive integer, you just times the base, this number, by itself this many times. So 2 to the power of 5 is 2 times itself 5 times. So we say that this is expanded form. Expanded probably because it's very, very long. Okay, so if a question in your test asks you in index form, you need to write it like this, where you should have something to the power of something. If it says write in expanded form, you write it out like that. Now, only if the question says evaluate should you actually give the numerical number, because 2 times itself 5 times actually equals 32. So that's what you would write if the question said evaluate, give a value to. Okay, now we're going to look at the index laws. So there's 6 index laws that you need to know. So make sure you understand that all of these laws involve combination of multiplying, dividing, and raising to a power, not adding or subtracting. So the first law we went through, if you multiply bases together, you keep the same base, and you add the indices together. Second law is if you divide bases, again you keep the same base, but this time you subtract the indices. So the rest of the laws follow in some way from the first 2 laws. So next up we have a power, so a to the power of b, and we raise it to another power. In that case, keep the same base and multiply the indices. The fourth index law is a consequence of the second one. It's if a is not equal to 0, then a to the power of 0 equals 1. So 1 to the power of 0 is 1, 2 to the power of 0 is 1, 3 to the power of 0 is 1, minus 1.257 to the power of 0 is 1. The only exception is 0 to the power of 0 is undefined. So the fifth law involves fractions. So when you raise a fraction to a power, you simply raise the numerator, the top thing to that power, raise the bottom thing to that power, write it without brackets. And the last one involves products. So if you have a product, a times b, and raise it to a power, then you just raise the first thing in the product to the power and the second thing, the product in the product to that power. So you can feel free to pause and copy down this index laws. Let's look at some examples. So we'll start off with some really easy ones. I'm going to write all my answers here in index form, except where I can evaluate. So first example, if I have, say, x to the power of 7 times x to the power of 5, I'm multiplying bases together, so that is just x to the power of 12. So second one, if I have an expression like that, but with numbers as well, I do the numbers separately. So if I have 2y to the power of 4 times 4y to the power of 7, I do the numbers separately. 2 times 4 is 8, and then y to the power of 4 times y to the power of 7, keep the same base and add the indices. So I can do that because the order in which you multiply things doesn't matter. Okay, so if I have something like 20x squared divided by 5x, again, do the numbers separately. 20 divided by 5 is 4, x squared divided by x is just x, because x is the same as x to the power of 1. So sometimes you might find it easier to write a division as a fraction. So let's say I have 12a squared b squared divided by 20ab. It might be easier for you to write this as a fraction. Now, when you're doing fractions, you can simplify the numbers as normals, and you can use your calculator to do that. So 12 over 20 is 3 over 5. A squared divided by a is a, b squared divided by b is b. Sometimes you will have an expression on the bottom. So if I have something like 18 x squared divided by 6x to the power of 4. So I have 18x squared on top, 6x to the power of 4 on the bottom. So 18 divided by 6 is 3 on top. But if I'm doing x squared divided by x4, the x squared will be on the bottom. So I can operate cancelling when I am simplifying divisions. Okay, so we'll look at the third law. If you have something like, doesn't matter whether it's a letter or a number, 3 to the power of 7 to the power of 4, keep the same base, and then multiply the indices. Okay, so I'm going to rub these examples out and do a few more, so please pause and copy down if you need them. So let's look at a few more examples and we'll look at the other laws. So the zero index law looks very simple, but it can be a bit tricky. So we know that something like 2 to the power of 0, that's just 1, that's easy. Let's say, for example, though, that I have something like 6t to the power of 0, and when I have a polynomial, I should stipulate that t does not equal 0. Okay, so we have to make sure we get our order of operations right. Raised to a power comes before multiplication. So the order of operations, brackets first, then raised to a power. So we have to do the thing circled first. So this would actually equal 6 times 1, because t to the power of 0 is 1, which just equals 6. But if you have something like this that looks similar, but is in brackets, so that means I now need to do the multiplication first, then get my answer, and raise to the power of 0. So if t does not equal 0 here, this thing here will not equal 0, and therefore it just equals 1. So if you have heaps of things inside the brackets and you raise it to the power of 0, it always equals 1. So if we have something like a fraction, like let's say x over y to the power of 5, we can of course write that in expanded form if we want. It's just x over y times itself 5 times, okay? And you may get asked to write something like that in expanded form. So when we multiply fractions, we just multiply the tops together, and we just multiply the bottoms together. So x times itself 5 times, y times itself 5 times. So notice I've just raised x to the power and y to the power. How easy is that? Now, if you have something like this, let's say 2x to the power of 4. A lot of people mess this up. What they do is they say that the answer is 2x to the power of 4. Now that's actually wrong, because what people are doing here, they're raising x to the power of 4, but they're not raising 2 to the power of 4. You must also raise 2 to the power of 4, and that just gives you 16. So 2x all raised to the power of 4 is 16x to the power of 4. So I've shown you some simple examples. Let's go ahead and look at some examples that are more complicated, that use more than one index law. So let's have something like this, x to the power of 4 times x to the power of 9 divided by x to the power of 7. Okay, so I do the top. To do the top, I need to use the first index law, so keep the same base, add the powers, and then I divide by the thing on the bottom. So I keep the same base and I subtract the powers, and x to the power of 6 is my final answer. So let's say I have something like this, x squared y to the power of 4, and I raise that to the power of 3. So here I need to use two index laws. I'm raising powers to another power, so that's 1, but I've also got a product inside the brackets. It's x squared times y to the power of 4. So what I do, using that index law I just mentioned, I take the first thing and raise it to a power times the second thing in the brackets and raise that to a power. You don't have to show this line of working, I'm just showing you to hopefully explain it a bit better. So x squared to the power of 3, keep the same base, multiply the powers. Y to the power of 4 to the power of 3, keep the same base, and multiply the powers. Similar thing works if you have something in a fraction. So let's say I have 2x over y cubed to the power of 5. So I have a fraction, I need to use that index law. So if I raise the top to the power, remember I have to raise everything on the top. So I go 2 to the power of 5, which is 32, and then raise x to the power of 5, and I raise the bottom to a power. So y cubed to the power of 5 is, of course, y to the power of 15. Sometimes you'll have to simplify things that are a little hard. They have a lot of things going on. So let's say I have something like x squared to the power of 0 times So let's say I have something like this. So again, note your order of operations and do the brackets first. So x squared to the power of 0 is just 1 times 12x to the power of 5. And on the bottom, I go 2 to the power of 6, which is 64. X to the power of 6 is, of course, x to the power of 6. So 12 over 64, I can simplify that. Use your calculator if you're not sure how to do it. So that just is 3 over 16. And x to the power of 5 divide x to the power of 6. So because there's more x's on the bottom, one more x on the bottom, I put an x on the bottom. And there I have my answer. So make sure you also understand a bit more about why the index laws. It turns out that you only need a couple of them because the rest follow from them. And I'll show you some examples of that now. So we really only needed these two index laws because the rest follow from them. So let's look at the third one, raising a power to a power. So if I have something like x squared to the power of 4, I can write that in expanded form. I times this by itself 4 times. So this law works. The reason that I multiply the powers is because if I write this in expanded form, I can just use the first index law. Keep the same base, add the powers 2 plus 2 plus 2 plus 2 is 8. So what I've done is I've added up this number this many times, and that's the same as multiplying. So it works for the zero index law as well. So why does x to the power of 0 equal 1? It's because of the second index law. So I know that x to the power of, say, 4 divided by x to the power of 4, keep the same base, subtract the powers. But anything divided by itself is equal to 1 except 0. 0 is the only number that you can't divide by itself and get 1. So if x isn't 0, I have something divided by itself, which is equal to 1. It's also equal to x to the power of 0 by the second index law, and that is why it works. If you want to know why the fraction or index ones work, so let's say I have a over b, and I'll just say to the power of 3. Well, that's actually just a over b times a over b times a over b. Okay, now the reason this works is we've got 1 plus 1 plus 1. We multiply the tops of fractions. 1 plus 1 plus 1 is 3. Same with the bottom. Okay, if I put a 2 here, I would still rely on the first index law. If I change all them to 2's, then on the bottom I would get b to the power of 2 plus 2 plus 2, which is 6. So the reason that this index law works is because of the first index law. So the last index law we used was a product. So let's say I have AB to the power of 5. So that actually works because it doesn't matter the order in which we multiply things. So we can write this as AB times by itself 5 times. But of course, I can rewrite this because it doesn't matter the order in which I multiply as A times itself 5 times B times itself 5 times, okay? And of course, by definition, and also using the first index law, all the a's together make up a to the power of 5, all the b's together make b to the power of 5. And it would work if I changed the powers here of a and b. So I just wanted to explain why some of the index laws work, because if you are able to get to that stage, and I know not everybody will be, then you'll be able to remember them a lot better and answer the questions a lot more confidently. The last thing I want to say is, with that last index law, it allows us to actually multiply numbers that are not the same base but have the same power. So because of the last index law, something like 12 to the power of x equals 4 to the power of x times 3 to the power of x. That's just using the last index law, the one I termed 6 before. For example, 18 to the power of x would be 9 to the power of x times 2 to the power of x. That's just following from the last index law. Okay, I've probably spoken enough about indices. Let's do scientific notation. So let's now look at scientific notation. So what we use it for really large numbers or really small numbers. And we do this to make the numbers easy to understand. So rather than have a number with just heaps and heaps and heaps of digits, we write it in a convenient way that allows us to compare numbers better. So when we write a number in scientific notation, we always follow the same format. So it's something, some number, times 10 to the power of something. So we really just need to figure out which numbers go in each box. So in the first box goes a number between and including 1 and 10. It can be a decimal, doesn't need to be a whole number. The number that goes in the second box is always a whole number, and it can be positive or negative. So by writing numbers like this, it allows us to check the numbers and compare them a lot easier. So let's go ahead and look at an example. So let's say I have the number here, which has quite a lot of digits. So this number is 6,275,000, and that's not a huge number, but obviously we can still write it in scientific notation. So it's a whole number, so I can write the decimal point here without changing the number. So I follow the steps that are in blue. Step 1, I'm going to move the decimal point until the number's between 1 and 10. If I move the decimal point to here and put it there, the number would still be quite a large number. It's 627,500. So I need to move it again, to second spot now, 3, 4, 5, and if I move it 6 spots, the number becomes 6.275. So that's a number between 1 and 10. So that is the number that goes in the black box. That's what the number that goes at the start. And it's always times 10 to the power of something. Now I moved the decimal point 6 spots. So a 6 goes here. It's a positive 6 because I moved the decimal point to the left. So I'm done. This number here and this number here are the exact same number. It's just that this will be easier to compare with numbers that have lots and lots of digits. So let's look at an example of a number that is less than 1. So let's say I have 0.0000325. Okay, so that's a very, very small number. So we can write it in a more convenient way rather than having lots of zeros. So we do the same process. We move the decimal point 1, 2, 3, 4. If I move it 5 spots, the number becomes 3.25. It's always times 10 to the power of something. In this case, because I moved the decimal spot 5 spots, I put a 5 up there, but I move the decimal point to the right, so the power is actually negative. So this number and this number are the exact same number, but this is written in scientific notation. Now sometimes when you write things in scientific notation, you'll have to round to significant figures. So significant figures similar to, but they're also different to decimal places. So remember, it can get a little complicated. So for significant figures, we don't count zeros at the start of the number. So in this number that I just converted into scientific notation, none of these are significant figures. We sometimes count zeros at the end of a number, which makes it very, very tricky as well. We count zeros when they're between a number, and that's why it can get a little tricky. So 3.25 times 10 to the power of negative 5. That has 1, 2, 3 significant figures. If I wanted to round it to 2 significant figures, I go 1 significant figure, and then the second significant figure is 2, but the next one is 5. I still use the rule 5 or more, raise the score. So to 2 significant figures, 0.000325 is 3.3. times 10 to the power of negative 5, okay? And this thing here doesn't impact on the number of significant figures. They all come from the decimal number. So obviously this number here has 1, 2, 3, 4 significant figures. If I wanted to round it to 2 significant figures, it would be 6.3 times 10 to the power of 6. Okay, so just make sure you know 2 significant figures doesn't mean 2 numbers after the decimal point. Now, if I have something like 1.042 times 10 to the power of, say, 20, for example, So this 0 does count as a significant figure because it's between two non-zero numbers. But if I had a number 0.042 times, say, 10 to the power of 20, that only has two significant figures, 1, 2. In this case, I wouldn't count that 0. So I've found many good videos on YouTube on significant figures, so please watch one of them if you want to find out more information on how to round numbers to significant figures. Other than that, I will leave you to study. Best of luck. This has been the luckiest maths teacher in the world. Have a great day.